Hello there, Mr. Sutton here with the BC Calculus 8-4 Extra Practice number 2 solutions on vector free response practice. For this one, we have a toy train moving along a straight track on a table. Position of the track, x of t, is measured in centimeters from the center, and at time 1 our train is 6 centimeters to the left. So x of 1 equals -6. Thanks for that. Time interval from 0 to 4, velocity is given by this v of t function. Alright, so for our first setup here, we want to figure out x of t, a function for x of t between time 0 and 4. So there's a few different ways to do this, but I'm going to go ahead and use differential equations. So v of t, that gives us part of what we need. If we took the antiderivative of this and then figured out an initial value, we could use that to come up with the x of t function. So taking the antiderivative of this, so I'm starting, that's my starting point here. On the left side, antiderivative of velocity, which is really x prime. Velocity is x prime, so its antiderivative is just going to be x of t. On the right side, we've got, let's see, this bumps up to a 3. Dividing by that, we have t cubed minus 12t plus c. And now they give us the initial value, x of 1 equals -6. So I can say then -6 for the x value over here, and then I'll plug in 1 for all the t values. So on the right side, I've got 1 minus 12, which is -11. Adding that over here, we get a c value of 5. So then I can write x of t equals t cubed minus 12t plus 5. For this part of the problem, they want the total distance traveled by the train on the interval from 0 to 4. So the key here is figuring out whether or not there are direction changes. That's what makes it total distance versus just displacement. So to find direction changes, I need to look at my velocity, which they gave me here, and figure out if there are any critical values, and then do maybe a little sign analysis to see if we have a real direction change. So I'm going to take 3t squared minus 12 and set that equal to 0 to find critical values. Now I can solve this by factoring out a 3. And then if I split this up by factoring, I've got t plus 2, t minus 2, which gives me negative and positive 2 as my critical values. Now the only one I actually care about is positive 2. Negative 2 is not on the interval from 0 to 4. It's before time began on this problem. But we do need to test out values around positive 2. So let me test out the value v of 1. If I plug in 1 to my velocity formula, that's going to come out, let's see here. You could use either this factored version or this version up here. Either one, pretty easy. That comes out negative. And then v of something bigger than 2, between 2 and 4, so v of 3. V of 3, if you plug that in, well, that's like 27 minus 12. That's positive. We have a sign change. That means we have a direction change at t equals 2. That means we're going to need to use two different integrals. And we're going to have to make sure that we get the absolute value of both of them so that we're not counting distance in one direction against distance in the other direction. So for my total distance then, I'm going to have the absolute value of the integral from 0 to 2, my direction change, of my velocity function, 3t squared minus 12. And I'll write out the whole thing because I'm going to have to do this by hand. This is a no calculator problem. Plus, I need the absolute value of the integral from 2 to 4 of the same function. Now, the only difference between these functions is that one of these is going to give us negative distance, the other is going to give us positive distance. So we're just making sure that they both give us positive distance. All right, so antiderivative time for this first one. Well, we already actually did this on the last problem, right? This is going to be t cubed minus 12t, evaluated from 0 to 2, absolute value of all that. Plus, this thing over here is pretty much exactly the same, only we're evaluating it from 2 to 4. So I've got absolute value of all this stuff with 2 plugged in, minus all this stuff with 0 plugged in, plus absolute value of all this stuff with 4 plugged in, minus all this stuff with 2 plugged in. Going left to right here, we've got, let's see, this is absolute value of, this is 8 minus 24, so this is -16 inside there. This stuff is just 0, so -16 is all I have in that absolute value. Over here, I've got 64 minus 48, so that's positive 16. This one here is, again, negative 16, but we're adding it. So this is absolute value of 16 plus 16, which is 32. So I have 16 plus 32 for a grand total of 48, and that was distance. So let's see here. What units should we use on this one? That's going to be centimeters. For this part of the problem, we now have a toy bus moving on the same table. Its position is given by x of t, y of t. X of t, they're telling us, was the function that we found in part A. And then y of t is this function, which is the distance from the bus to the train track. Since our train track was running, I guess, more or less horizontally, you could think of this as kind of like the y value, and it literally says y of t. So we want an expression, but we don't have to evaluate it, for the total distance traveled by our bus during this interval. Well, total distance, setting up our parametric total distance kind of thing, we're just going to have the integral from 0 to 4 of square root of x prime of t plus a squared plus y prime of t squared. But that means we need to actually spell out what x prime and y prime are. Okay, well, let's go ahead and get x prime. They said that x of t was the function that we just figured out in part A. Well, that function came from taking the antiderivative of this velocity formula here. So that means that x prime is actually just going to be this velocity formula from part A. So x prime is just going to be 3t squared minus 12. All right, now how about y prime? Well, that we just directly differentiate the y function here. 2 goes away. We've got, let's see here, 12 cosine of t over 4 times a tail of 1/4. So that's going to be 3 cosine of t over 4. So we've spelled out x prime, y prime. The distance now, the total distance traveled by our bus, again, is going to be our integral over the time interval. So integral from 0 to 4 of square root of x prime squared plus y prime squared dt. And we didn't have to evaluate it, so we've finished this part of the problem. On this no calculator problem, we have a particle moving along a curve defined by this equation right here, and the x-coordinate satisfies this differential equation with initial condition 0, negative 4. First part of the problem, we want to find x of t. So basically, we have to solve this differential equation. To make that a little bit easier, I'm going to rewrite the right side here as 2t plus 1 to the negative 1/2 power. And I'm also just going to multiply both sides by dt just to get that over there. We don't really need to do separation of variables on this one, but hey, why not? Get the t's with the t's. Okay, so taking the antiderivative, I've got just x of t on the left side. On the right side, I have to use my reverse power rule, so I have negative 1/2 being bumped up to the 1/2 power. Dividing by 1/2 gives us multiplying by 2, so I've got 2 times all this stuff to the positive 1/2. But we have an inner function of 2t plus 1, so I have to divide by that inner tail of 2. So multiply by 1/2 out here. And I also have a plus c, of course. So at this point, the 2 here and the 1/2 end up canceling. We just have the square root of 2t plus 1. We also have to figure out the c value. So if negative 4 is the x value, then I can plug 0 in for the t value here. So I can write this as square root of 2 times 0 plus 1 plus c. Well, this is just the square root of 1, which is just 1. Subtracting from both sides, we have c equals negative 5. And there's nothing to really resolve. I just have to plug this back in. So I can write x of t then equals square root of 2t plus 1 minus 5. For this next part of the problem, they want us to find dy over dt in terms of t. There's a few ways to do this. One way you might think about doing this is differentiating implicitly with this equation up here, and then doing some kind of substitution for the dx over dt. Another way you could do it, which I actually did, since we already figured out what x of t equals, why don't we just replace the x here with this x of t expression, so get it all in terms of t. Then, once we have an equation with just y's and t's in it, take the derivative with respect to t. So that's what I did. I rewrote this as y equals all this stuff to the third power minus 3 times all that stuff. So distributing that minus 3, we've got minus 3 times 2t plus 1 to the 1/2, and then negative 3 times the negative 5 here is going to be positive 15. Now taking the derivative, going from left to right, this first thing I'm going to need the chain rule, so I have something to the third power. That derivative is going to be 3 times the something squared. Now I have to multiply by the derivative of the something. That's the stuff in here. The negative 5 is not going to matter. That's just 0. But this 2t plus 1 to the 1/2, that's going to be 1/2 times all this stuff to the negative 1/2 times the derivative of 2t plus 1, so another chain rule. So that's times 2 when all is said and done. Now for this next piece here, this is just a power rule with a chain involved. So this is going to be negative 3 over 2, 2t plus 1 to the negative 1/2, times the derivative of the inner function, so times 2 there. And then derivative of 15 is conveniently 0. All right, so I've actually finished the problem. We've expressed dy over dt in terms of t. We don't have to simplify it. But if you look ahead later on, you're going to see that you actually do kind of need this simplified in order to use it. So I'm going to simplify, but you could wait until later to do it. But I'm going to do it now. So when I'm simplifying this, I notice that I have some things with negative exponents, which means there's some things that should end up downstairs if I turn this into a fraction. Upstairs, I've got this 3 times all of this stuff to the second power. So I'm going to write a numerator with 3 times square root of 2t plus 1 minus 5, all of that squared. And let's see here. I'm bringing this stuff downstairs. So I've got a 2 downstairs already. I've also got the square root of 2t plus 1 downstairs. So 2 radical 2t plus 1. And it looks like actually this 2 downstairs and this 2 upstairs are going to cancel, so I'm not going to bother writing that down there. Next up, and this is kind of interesting, this is, let's see, this 2 and this 2 cancel, so you really have minus 3 over radical 2t plus 1. That happens to be the same denominator as we have right here. So if I'm subtracting 3 over this stuff, why don't I just move that minus 3 into the numerator there? So this is the fully simplified version of this that we're now going to use in later parts of the problem. On this problem part, they want the location and speed of our particle at time 4. So for this problem, I'm going to need some past pieces of information here. If I need the location, I'm going to need that x of t function that I wrote back in the day. So there it is again, 2t plus 1 to the 1/2 minus 5, or radical 2t plus 1 minus 5. And if I want the speed, I'm also going to have to talk about dy over dt. So here is that, the simplified version again, y prime of t. Now to get the location, let me start by just plugging 4 into this x function here, because y is defined in terms of x. So if I find the x value by plugging 4 into here, I can then use that x value and figure out the y value from that without even having to know y of t. So plugging 4 in there, we've got square root of, let's see here, this is going to be 9, so that's 3. Subtract 5 from that, we have negative 2. So that's the x value. The y value I'm going to get by just plugging this back into the y equation here. So y is going to equal negative 2 cubed minus 3 times negative 2. This is negative 8 plus 6, which is negative 2. It's kind of interesting. So our location then is negative 2 comma negative 2. Now we need the speed. To get the speed, I need the square root of x prime of 4 squared plus y prime of 4 squared. Well, that means I need x prime and y prime of 4. So let me go ahead and find each of those. For x prime, I just need to plug 4 into dx over dt. So 1 over the square root of 2 times 4 plus 1. Well, this is really just 1 over 3, because this is the square root of 9 again. So that's not so bad. We also need y prime of 4. So for that, I have to use this equation I came up with up here. Now, this is the reason I simplified this thing, because I knew just reading ahead that I'd have to plug something into it. So let's plug 4 into all of that craziness there. So this is just one big PEMDAS problem, in case you were wondering if you were ever going to need kind of order of operation PEMDAS. You don't necessarily need to simplify this. I guess you could write this as like some constant and then just use that constant inside your square root later on. But it seems kind of unfulfilling to do that. So let's simplify it. So we've got, let's see, innermost stuff here. Square root of 9 is 3. 3 minus 5 is negative 2. So we have 3 times negative 2 squared minus 3 all over square root of 9 again down here is 3. Next, let's see here. I actually can be really fancy and cancel out these 3's because I've got 3's in both terms. So this is just going to be then 4 minus 1, which comes out to 3. Or I guess you could do 12 minus 3 is 9 divided by 3 is 3. Either way. So now these are the two things I need to square inside a square root. So speed then is going to be x prime of 4 squared plus y prime of 4 squared in general. So in particular, we've got 1/3 being squared along with 3, and those are being added together and square rooted. This is a constant. We could just leave it like this, or we could simplify more. So this is 1/9 plus 9, or 81/9. 1/9 plus 81/9 is 82/9. So that's what we end up taking the square root of. And I guess if you wanted to really keep going, you could do like a radical 82 over 3, but whatever. I think this is good enough. On this calculator-based problem, we have a particle starting at point A in this graph, and it travels along this curve from A to B to C to D as time increases. So coordinates of position are x of t, y of t, and we've got an x prime and we've got a y prime that's actually not explicitly given. And then at time 9, they're saying we reach point D on the positive x-axis. Okay, so let's start with part A here. At point C, that's right here, is dy over d positive? How about dx over dt? Give a reason. All right, so we basically need to figure out what y is doing as time increases. And for that, you have to read closely here because they said we're starting at point A and going this way. So that means that at point C, we're going down and to the left. In general, that means in terms of y is decreasing as t increases. Well, if y is going down, if we're going down as the time goes on, that means that dy over dt cannot be positive. In fact, it's got to be negative. So for that reason, dy over dt is not positive. Now at point C, we can talk about x. We're going left, so that means that x is decreasing, x of t is decreasing as time increases. So dx over dt cannot be positive either because these things are going opposite directions. Time is going up, x's are going down. So that would be a negative slope. So then we can write dx over dt is not positive. For this problem part, they're telling us the slope of the curve is undefined at point B. At what time t is the particle at point B? So, I mean, they're not telling us anything we didn't really already know. This is a cusp of sorts. So, yeah, we have an undefined slope there. But we want to know at what time we reach that spot. So we're going to use the fact that we have an undefined slope to narrow down the time that it could be. Now, in general, dy over dx in terms of these parametrics here is really y prime over x prime. So if we have an undefined overall slope, that means the x prime here must take on a value of 0. Well, what value of t makes this dx over d come out to 0? For that, we can use the calculator. So here I am on my calculator. I've taken the time to enter dy or dx over dt in my y1, and that was kind of a pain because there's a lot going on there, but it'll be worth it. Now let me go to my window to graph this thing. And for the interval, they said that we got to point D at time 9. So there's really no point in graphing this beyond 9. So let's go 0 to 9. And then zoom fit, zoom 0. And let's hope for the best. All right, so there we go. There's the graph of x prime. Very nice. So taking a look at this, it looks like dx over dt equals 0 right about here. And the other spot I think happens at the very end of the interval. Let's go and see what that exact spot is. So if I do, let's see, second trace zeros, let's see if we can calculate it. So we're going to go a little bit to the left, a little bit to the right. Press enter one more time and hope for the best. And it's thinking. That's never a good sign. No sign change. Interesting. Okay, so how do we fix that? Well, I'm going to go with actually plugging in what I think this value is and see if that works. So that looks like a value of 3. So let me quit out, and let me just do alpha trace y equals y1. That's where I stored my x prime. Let's plug in 3 and see if it comes out to 0. If it doesn't, then we'll know that it was a near miss, and we can zoom in and see what else is going on. Oh, I do get 0. So this is just a weirdness with the calculator. For whatever reason, our calculator is not going to find the 0 with calc 0. So we just figure out that it's 3, plug it in to confirm. So then we can say dx over dt equals 0 at time 3. Therefore, this is the time at which we are at point B. For this problem part, they're telling us the line to the curve at the tangent, line tangent to the curve at the point x of 8, y of 8 has this equation here. Looks like a friendly y equals mx plus b kind of setup. They want us to find the velocity vector and speed of the particle at this point. Well, just thinking in terms of what we need for these, for velocity vector and speed, we need to know x prime of 8 and y prime of 8. We know x prime of 8, or at least we could figure it out. This is x prime right here. We have this in our calculator. We can just plug 8 into this thing to get a value back. In fact, let's do that now. So remember, on my calculator, I stored x prime as my y1. So I'm just doing y1 of 8 then, giving me, okay, negative 4.5. I probably could have gotten that eventually by just plugging in 8 to all this stuff, but it's so much nicer to have the calculator handle all that heavy mental lifting for me. So there's my x prime of 8 that I'm going to have to plug into as both a part of a velocity vector and also in that speed formula. But I still need y prime of 8. And the trouble here is that y prime is not explicitly given. So we're going to have to figure out y prime. The good news is we can use x prime of 8 to do that. And also this little bit about the line tangent to the curve at 8 having this equation. So we know that in general, the derivative of our curve at 8 is going to be y prime of 8 over x prime of 8. This is just the way our parametric derivatives work. We also know that the derivative of the curve at 8 ought to have a value based off of this tangent line equation of 5 over 9. That's the slope of this line. So I can use this information and the fact that I already know x prime of 8, remember it was negative 4.5, I can use that information to figure out y prime of 8. So if I do that, just multiply both sides by negative 4.5 and divide by 9. Let's see what I get. Now, I probably don't need the calculator. I should use the calculator, but I can do it without it. Negative 4.5, if I'm multiplying up here, divide that by 9, that's going to be negative 0.5. 5 times negative 0.5 comes out to negative 2.5. There we go. Who needs a calculator? Well, we will in a minute. But for now, we've got negative 2.5. So my velocity vector then is just going to be x prime of 8 comma y prime of 8. So negative 4.5 comma negative 2.5. That was pretty straightforward. For the speed, again, I need the square root of x prime of 8 squared plus y prime of 8 squared. I am definitely going to use the calculator on this. So here's what that looks like on the calculator. Recall we already found x prime of 8. It's just negative 4.5. And then we found that y prime of 8 was negative 2.5. So squaring those, adding them together, square rooting it, we end up with about 5.148. For this last part of the problem, we want to know how far apart are points A and D. Now, the key on this one, I mean, if you just were given 2 random points and needed the distance, you could use the distance formula, square root of x2 minus x1 squared plus y2 minus y1 squared and all that jazz. But we don't even need to do that much work on this because these points are both on the x-axis, which means we don't have to worry about the vertical distance in their difference. We just have a horizontal distance to calculate. Well, how can we find the horizontal distance? Since these are both on the x-axis, how can we figure out the net horizontal change, I guess is how you could think about this. Net positive change in x of t. Well, that net change happens over the time interval from 0 to 9 seconds. We have this x of t function that's moving us different places. So if I just want the net positive change, I just need to integrate the derivative of x over that time interval. So I'm going to just write the absolute value of integral from 0 to 9 of x prime of t dt. 0 to 9 integral x prime of t dt, that's just going to give me the net change, but again, I want to make that positive, so there's the absolute value. Let me plug this in the calculator now. So I'm going to do, let's see, alpha window and use the absolute value there. And then we're going to do math 9 to get my integral from 0 to 9. And then let me do alpha trace y1. That's where I stored x prime dx. All comes out to a grand total of 39.255.